In this next video, we're going to talk about this idea of a Fisher projection. Um, Much like how a Newman projection was just a different way to look at a molecule, so is a Fisher projection. And a Newman projection was looking along a direct bond, like a carbon-2, carbon-3. A Fisher projection is going to be looking at something almost like from the top. So let's go ahead and zoom me in. So here we have, like, for example, a normal zigzag. So we have a black carbon and then just a blue and a purple to show, sorry, a red and a purple to show different. Normally when we draw that zigzag, you'd have like wedges and dashes for going like into the page and out of the page. What a Fisher projection is going to do is it's going to rotate it so the entire backbone is going to be vertical. And with this, we're going to have nothing actually in the plane. So if we focus in the point of view of just like this carbon here, the two hydrogens here that used to be kind of wedges and dashes, they are now coming right at you to try and like give you a hug. So both of these are actually going out of the plane or like towards you. And then the red and the purple ball are both going away from you. So you're going to have two things that are left and right, which are going to be wedges coming out at you, and then two things top and bottom, which are going to be dashes going away from you. Now, to draw that, we would go through and we would normally have an image like we have over here on the right side, where you'd have your central carbon, the two things on your left and your right, which are your X and your Z, they're coming out towards you. They're the ones trying to like give you a hug. And then your top and your bottom, your W and your Y, are like where that the red and the purple balls are, and they're like going away from you. However, this is a lot of wedges and dashes to draw. So for a Fisher projection, what we're going to do is we're just going to draw normal solid lines, but have a understanding that things on the top and bottom are going to be dashes and things on the left and right are going to be wedges. So a Fisher projection is going to look at the image on the left-hand side where we have a cross. We know that this right here being an apex is going to be where our carbon is. Anything that's going to be the left and the right, we're going to define as a wedge, and then anything on the up and down, we're going to define as a dash. And these are going to be just two kind of understood things, much like how in a skeletal structure we don't draw hydrogens, we just assume they're in. Here, we're not going to draw the stereochemistry, we're just going to assume that it exists. And with this, one thing that we're going to have to do a lot is we're going to go through and we're going to do our normal RNS configuration. So there's going to be 4 different groups we're going to look at. I want to rank them 1, 2, 3, 4. However, the only time which your 4th group can be in the back is going to be if it's on the top or the bottom. And by practice, it's never like that. Almost always it's going to be in like the X or the Z position. And with that, we're going to do kind of like the opposite of all of them. So if it looks clockwise, it's actually counterclockwise kind of thing. Now, on the next, in the notes, I've gone through and there's actually only 4 physical cases that you can have for the possible arrangements of your different groups. And here I have all of them and what they actually are they R or S. However, we don't need to go through and memorize a bunch of these random cases. We can use just our normal process that we've been going through in all of our past videos. So here I have kind of example of Fisher projection, and we'll notice that this is going to have a total of 1, 2, 3, 4 carbons, which are not drawn in, each shown as the red dot. Each of those can be a chiral center because they have 4 unique attachments with stereochemistry, that is wedges and dashes, that are defined, even though they aren't shown. And therefore, we can have 4 different spots where we could have an R or an S configuration. And let's go ahead and look at each of these and then kind of get some practice on thinking about how to kind of understand this idea of a Fisher projection. So let's go ahead and start by just looking at just this top one right here. So I'm just going to redraw just a little section of it over here. So I have a cyano, I have an H, an OH, and at the bottom I have a carbon. And this carbon, and maybe let's go ahead and call this carbon 1, carbon 2, carbon 3, carbon 4, is going to be my carbon 2. And attached to that carbon 2, I'm going to already go ahead and give the different names, the different identities. So we have an oxygen on the right, a carbon on the bottom, and then a hydrogen on the left. Now, the other thing to think about is that cyano. I wrote just CN, but a cyano is a triple bond to a nitrogen. So in terms of writing it, we're going to write a carbon connected to a nitrogen, connected to a nitrogen, connected to a nitrogen. And it's going to be 3 kind of separate nitrogens because there are going to be 3 different bonds. So let's go ahead and rank these through our Kahn-Ingold-Prelog rules. And our very first thing we're going to do is we're going to look at the very first atom that's going to be connected to our carbon 1. And we have, starting at kind of noon, we have a carbon, and then oxygen, carbon, and hydrogen. So our hydrogen we know is going to be the smallest, so we're going to go ahead and give that an assessment of a 4. And we know our oxygen is going to be our biggest. I'm struggling here. Still struggling here. I'm moving things too. We know our oxygen is going to be our biggest, based on where it is on the periodic table. It has a higher atomic number than carbon. And then our 2 carbons are going to be our second and our thirds. So looking at it, we have a carbon with a nitrogen and a carbon with an oxygen. And when we think about the periodic table, our oxygen is going to have higher priority than our nitrogen. So we're going to put a 2 down here and a 3 down here because we're going to be comparing that oxygen and the nitrogen. And it goes carbon, nitrogen, oxygen. Carbon wants 4 bonds, nitrogen wants 3 bonds, oxygen wants 2 bonds, and then something like a fluorine or chlorine wants 1 bond. So we're kind of going to the right there on the periodic table. We can then go through and figure out our rotation. So we're going to go from 1 through to up to 3. That rotation right there is going to be a clockwise rotation. And a clockwise rotation is normally R. However, our 4th group here is not in the back. Our 4th group is actually a dash. Or sorry, it's a wedge. It's not a dash, I should say. So we have a wedge for our 4th group because it's on the left and right, and those left and right are looking like they're going to come and hug you. So even though this looks like it's clockwise, it's actually counterclockwise. And you can redraw this and rotate that all the way to the back, or you can just remember that if it's coming out at you, we just do the opposite. And counterclockwise things are S for our configuration. So we're going to say that that top one is an S configuration. And you can walk through these on all of your different carbon centers. Let's go and do another one for practice. Let's look over here at carbon 2. And let's go ahead and just draw this little subsection again. So we have a hydrogen over on one side. We have an oxygen on our right. On our top, we're going to have carbon 1. And on the bottom, we're going to have carbon 3. Let's write everything we know about carbon 1. So carbon 1 is connected to an oxygen. It is connected to a carbon. And it is connected to a hydrogen. If I look at carbon 3, it is connected to an oxygen, a carbon, and that's specifically carbon number 4, and a hydrogen. And if we look at those, both that carbon 1 and that carbon 3 are going to tie because we have a carbon, an oxygen, a carbon, and a hydrogen. Those are the same for all of those. That does not necessarily mean that this is going to be achiral. That just means we're going to follow rule number 2 one more time, and we're going to go one further. If we look at both of the oxygens, they both just go to a hydrogen. They're both just alcohols, so you kind of run out. So instead, we're now going to look at carbon 4 and the carbon at the top. And that carbon at the top is going to be our cyano. So that's going to be a carbon that is connected to a nitrogen, and a nitrogen. If I look down at the bottom, the carbon 4, see its attachments. So carbon 4 is connected to an oxygen, a carbon, and a hydrogen as well. So an oxygen, a carbon, and a hydrogen. That carbon is the one that's all the way down here. And now we have a point of difference that we can actually find out. And this is something that you have to do a lot in Fisher projections. A lot of times you're just going to have a bunch of carbon and hydrogen stuff, and you have to look pretty far out. We can go and do our rankings. So our oxygen is going to be number 1. Our hydrogen is going to be number 4. Here I do a carbon and a carbon, a tie. Oxygen and oxygen, they're going to tie. Carbon and carbon, they're going to tie. Hydrogen, hydrogen, they're going to tie. I would then look at the oxygen, which is connected to a hydrogen and a hydrogen, so they're going to tie. So then we'll look at this carbon and this carbon, they're going to tie. And now I finally have a point of difference between that nitrogen and the oxygen. And if we remember from the last one, our oxygen is going to be a larger number on our periodic table. So the carbon 3 is going to get a ranking of 2, and then carbon 1 is going to get a ranking of 3. So I can go in and I can see that this is going to have that same type of rotation. That same rotation is going to be clockwise, but my 4th group is on my left or right. Therefore, this is actually counterclockwise and is therefore an S. So carbon 1 is going to be an S and carbon 2 is going to be an S. And you can actually keep going through and doing the same exact process on all of these. Now, go ahead and pause the video and take a second to think about carbon 3 and carbon 4. Try to get an R or S configuration for each of those. Now, for each of these, I'm not going to go through them all. I'm just going to give you the kind of quick answers. So for our carbon 3, our rankings are going to be 1 at the oxygen, 4 at the hydrogen. Comparing our top and our bottom is going to get to the chlorine quicker. So it's going to have priority of 2 down here and 3 up here, giving a rotation that is going to be counterclockwise. However, our 4th group is on the right side, which means it's a wedge. So it's actually clockwise and gives you an R. And then for the bottom, you're going to have a 1 for your alcohol, 2 for your chlorine, because you're going to be comparing a chlorine and an oxygen, and that's going to win. So you're going to get 3 up here. So 1, 2 to 3 is going to follow that same rotation counterclockwise, but your 4th group is in the front, so therefore you would get an R. So overall, this entire molecule, and from top to bottom, has an S, S, R, R for its specific stereochemistry at each of those chiral carbons. Now, as a quick reminder, if we wanted to draw an enantiomer, an enantiomer is going to be switching every single one of those. So your enantiomer is going to be an RRSS. You can have a ton of diastereomers. Your diastereomers are going to be ones that are going to have some the same and then some the different. So just to give one example of a diastereomer, if I did maybe an S, so the same, and then an R, so different, and then maybe an R, so the same, and then maybe an S to be different. So an SRRS would be an example of a diastereomer, and there's a bunch of other examples of diastereomers. One of the easiest ways to convert something from an R to an S is just simply switching what's going to be on the left and what's going to be on the right. We're going to go ahead and stop there. In our next video, we're going to spend a little bit of time talking about how do we go from like Newmans to zigzags to Fishers and back and forth between them. And then in class, we'll spend a bunch of time doing a lot more practice on determining RNS of Fisher projections, as well as comparing 2 different Fisher projections and thinking about whether or not they are enantiomers, diastereomers, mesocompounds, and so on and so forth. So I will see you in the next one.